now that we have the completeness axiom, we're going to use it to prove theorems about real numbers. And the first one we're going to look at is something called the Archimedean property. So we're going to motivate and state the Archimedean property, what it means. We're going to go ahead and prove it for real numbers. And then we're going to use the Archimedean property to prove a theorem. All right, so suppose that we have two positive numbers a and b. The question that I want to ask is, can we find a large enough natural number n so that n times a is bigger than b? Specifically, can we do that even if a is a really small number or if b is a really big number? And from what we know about natural numbers, it's unbounded above, so certainly we should be able to find a natural number big enough no matter how small a is, no matter how big b is, so that n times a is bigger than b. Well, how would we prove it? Well, we're going to prove it by contradiction, right? So we're going to assume that it's not possible to find such a natural number, which means that we're assuming that n times a is less than or equal to b, no matter what natural number you choose, n. And if we look at that inequality, n times a less than or equal to b, that looks like an upper bound situation. It looks like b is an upper bound for all the possible natural number multiples of a that you have. So that suggests that maybe the completeness axiom can help us solve this problem. So we're going to define S to be all real numbers x, such that x is equal to n times a for some natural number n. So if we list out all those numbers, that's a, that's 2 times a, 3 times a, 4 times a, etc. And if we look at our contradiction assumption, that n times a is always less than or equal to b, that tells us that b is an upper bound of S. That tells us that S is bounded above, and by the completeness axiom, that means that S has a supremum. We'll call it beta. So remember, being a supremum means two things. First of all, beta is an upper bound of S. That means it's bigger than or equal to all multiples of a. And secondly, if we take any number that is smaller than beta, it is not an upper bound. And in particular, the smaller number than beta that we're going to be looking at is beta minus a. Remember, a is a positive number, so beta minus a is smaller than beta. By our assumption about beta, it's a supremum. That means beta minus a is not an upper bound of S. And what does it mean not to be an upper bound of S? That means there is some element in S, some n times a for a natural number, that is bigger than beta minus a. And if we add a to both sides of that inequality and flip it around, that means that beta is less than na plus a. If we factor out that a, that means that beta is less than n plus 1 times a. But here's the deal, that n plus 1, that is a natural number, which means that n plus 1 times a is in the set S. But since that n plus 1 times a is bigger than beta, that means that beta is not an upper bound of S. That's a contradiction. So that gives us the Archimedean property. If you have any two real numbers that are positive, a and b, then there exists some natural number n such that n times a is greater than b. All right, so let's go ahead and try to prove a theorem with the Archimedean property. This is actually going to be a really helpful theorem for us later on. We're going to let a and b be real numbers with a less than b, and we're going to prove that no matter how close those numbers are together, that there is a rational number in between them. All right, so here's what we want. We want some rational number, m over n, that's between a and b. And because a rational number can be is a ratio of two integers, even if n happens to be a negative integer, by multiplying top and bottom by -1, we can assume that n is greater than 0. That's going to be helpful to us. So if we then multiply all sides of the inequality by n, that's using scaling, that means that na is less than m is less than nb. So the question is, can we choose an n so that the na and the nb are far enough apart that we can squeeze an integer between those? Well, you're going to help me out on your homework with this. You're going to prove that anytime you have two numbers where when you subtract them you get a number bigger than 1, then you can always find an integer in between them, right? Now, if we factor out the n, that means that we're looking to find an n where n times b minus a is greater than 1. And as long as we can find that, we should be able to find that magical integer m. All right, and if you're looking at that n times b minus a is greater than 1, that looks exactly like the Archimedean property, where instead of b, you have 1, and instead of a, you have b minus a. Remember, b is bigger than a, so b minus a is a positive integer, or positive number. All right, yep, looks like Archimedean property. Let's do it. So our theorem is let a and b be real numbers with a less than b. Then there exists some q in the rational numbers with a less than q less than b. Let's do it. So we have a less than or equal or less than b. That means that b minus a is greater than 0. Also, 1 is greater than 0. 1 is a positive number, so we're set up for the Archimedean property. That means there exists some natural number n with n times b minus a being bigger than 1. If we multiply out that n through using the distributive property, we get nb minus na is greater than 1. By your homework result that you're going to help me with, I appreciate that, there exists some integer m with na less than m less than nb. And now we can use the scaling axiom to divide all sides of the inequality by n. We get a less than m over n less than b. If we let q be m over n, that is a rational number. And then we're done with the proof of the theorem. All right, so I think you're ready to work on the activities for the Archimedean property. You can find those at the link below this video.